Okay, hi, Bruce again. Welcome to lab number 2 for logic circuits. Okay, so in logic circuits number 2, we're looking at theorems and postulates for the logical functions, right? So one of the things that you kind of have to wrap your head around is that, you know, you've taken in math, there's like addition, subtraction, multiplication, division. Well, in logic, it just adds to it, right? You and, you or, exclusive or, all these different functions, right? And then, so what you have are different ways of simplifying or quantitatively measuring and designing logic circuits. Okay, so there's a whole bunch of them on the sheet. You know, you can look at it and you can go through all of these ones, right? And there's certain ones that kind of have a lot of different uses than what you just can think about, like from a logic standpoint, right? So one of them is A ANDed with 1 equals A. A ANDed with 0 equals 0. Okay? So you see this and you go, yeah, okay, whatever, right? But this has, I use this frequently, right? Because say, for example, like in more complicated logic circuits, when you start getting into synchronous logic circuits, everything synchronizes to a clock signal. So say you wanted to start driving a certain part of your logic with a clock and then shutting it off. Well, say here, we use our AND gate here, right? And so we have our clock signal here coming in on this input, okay? So if we were to ground this input here, basically we have nothing happening, right? But then after a certain amount of time, we want all of a sudden, we want now the clock to come through. So we switch this over to plus 5 volts, and then the clock starts coming through, right? And then after a while, we want it to stop, we take it back to ground, and it shuts off the clock again, right? Again, so here's a function of a logic gate that, again, like in the logic class, you're probably going to go through all this different logical, mathematical kind of stuff, right? But when it comes to actually designing logical circuits, things like this, I mean, you got to kind of know these things, right? And you need experience working with these circuits to kind of figure out all these different things, right? Okay, so no, I just wanted to show you that because like that's one of the things I use frequently, and you know, it's very useful. And yet it's kind of outside of the logical type of theory stuff, but it's something you use in a logic circuit all the time, right? Okay, and then we go through a lot of these other theorems and postulates, like absorption and commutative law and stuff like that. Those are all mathematical as well, right? Well, the same kind of principles apply, right? So say you had A, B, or C, and this equals A, B, or A, C. Again, that's just kind of logical, okay? Right? And you go through a lot of these other different theorems and that too. Again, they're all listed on the page, right? And then the other one I usually go through is as I go through De Morgan's theorem, right? So De Morgan, right? I call it the bubble theorem, okay? Because let's say we have an AND gate like this. Okay, and then say we want to convert that to an OR gate, right? So where we have our OR, okay, Okay? Here's our OR gate. So what De Morgan says is, wherever there's no bubbles, you put bubbles. Right? So we would call this a negated input NOR gate, right? But this is equivalent to an AND gate. Okay? And so if you had an inverter here, you don't have an inverter here, right? So again, wherever there's bubbles, you don't put bubbles, and vice versa. Okay? But now you're asking, like, so what? Why would I need to know this? Well, here's one of the things, right? So remember from lab number 1, I said on your IC, you have a certain number of gates on your IC. Right? So say, for example, you had an AND gate in your circuit, and you were using 2 of these AND gates. Well, there's still 2 more on this chip. And then say you needed an OR gate. Well, instead of using an OR gate, you could use another one of these AND gates, and that would eliminate one of the chips out of your circuit. You're saving money, right? Because now you're designing this circuit with only 1 chip instead of 2. Right? And again, like, this is where a lot of these things are coming into play, where we're trying to simplify the logic circuit. We're trying to make it as tight as possible, like with the fewest gates, but also more than that, the fewer chips, right? Because say, for example, say we needed, instead of 1 OR gate, we needed both of these ANDs. Well, we increased the number of AND gates, but we actually made it a cheaper circuit, which your boss is going to like, right? You're going to have a cheaper circuit because you're only using 1 chip instead of 2. Right? So these are the reasons why we go through and do this. Okay? So what I'm going to do is I'm going to go through and I'm going to do this for my demonstration, right? What we're going to do is we're going to go back and I'll use this okay? So what I'm going to do, right, is I'm going to build this circuit. I'm going to do the truth table, right? And then I'll build this circuit, and I'll do the truth table, and I'll compare them. And they should be the same, right? And again, we can go through that with all these different circuits and prove all of these different things, right? But that's just takes a lot of time. So we're just going to go with this 1 circuit here. This is what we're going to do. We're going to prove this theorem. And again, that's what you would be responsible for in your lab, right? All right? So, okay, so I'll meet you in the lab and we'll do our demonstration. Okay, so here we have the circuits for lab 2. Actually, I've got both connected up. There's not a lot of connections. And then I've got the first circuit wired to the microcontroller board. Okay, now one thing you might notice here is that the wires look kind of long. And they are. You shouldn't use long wires like that. It can pick up different electrical noise and stuff like that that can affect some of your signals. Now, for our purposes here, I don't think there's going to be any problem. But because I'm working at home right now, I don't want to butcher up, I've got limited resources, so I don't want to butcher up my long wires, cut them up, and then be short of long wires later. But if you're wiring this circuit up, hopefully you have better resources than I do at home right now, hopefully, and you can shorten up these leads and make it a little more pretty. Okay, so we'll go on to the demonstration here. The demonstration for lab number 2. I'm going to use logic bits 3, 4, and 5 for my inputs, okay? And logic bit 5 is going to be my A, all right? So we're doing A, ANDed with B or C, and B or C are in brackets, right? So you have to do that operation first. So anytime A is 0, the output is 0 because A is ANDed with the output of B or C. So all those will yield a 0. And then if B or C, if both of those are 0, well, that'll also yield a 0. And then the rest should be 1s. Okay? So what I've got now, I've got them all on 0s. Okay? So this is all 0s and the result is 0. I change C to a 1, I get a 0. Okay? Now I put C back. So this is B is 1, C is 0, A is still 0, and you get a 0. And then I've got both as 1s, but it's still 0. Okay, so now I'm going to put these back, and I move the A is now 1, and I measure, it's still a 0. Okay, now anytime I move any of these, so now C is 0, this should yield a 1. Okay, and there it is. Now B is 1, it yields a 1. And then when all three are 1s, okay, so that's what we're expecting. Okay, so now I'm going to move the leads over to the other circuit. And so this is A, is coming over to here. Okay. The output is coming to here. And then this is B. And then this is C. Okay. So I think I've got it set up. So I'll move these all back to 0s. Okay, and again, like A is going to be logic bit 5. So if I measure here, I get a 0. I set C to 1, but the output is still 0. I set B to 1, the output is 0. I set both of them to 1, the output is 0. Now I move the A to a 1, this should be 0. And now any of these should be a 1 now. And that's a 1. That's a 1. And that's a 1. Okay? So essentially what we've done, right? So this circuit, right, is A and B ORed with A and C, right? And again, that's one of the postulates that we talked about in the lab. And so what we've done is we've proved that to be true because both of the outputs are exactly the same. All right. So what you got to do is you have to design the circuits, right? Draw them out for me. Tell me the chips you need to build the circuits. And then I'd also like to see how you would connect them as well. So again, that's a little bit of work, but that's what I'm expecting to see from the lab report. All right. Okay, so thank you, and I'll see you in a week for lab number 3.